Okay, let's start. So what we did last time, we did a little bit of mathematics in the sense that we discussed Sobolev spaces, which are now the background of what we are doing. And the important thing to handle Sobolev spaces is actually it's not so difficult to handle them, because we have density results saying that certain spaces of C infinity functions are dense in the Sobolev spaces. These are either, if we have the zero version, so to speak, so these with the trace zero, these are just the test function in the sense that C infinity 0 of omega is dense, and in the other case we have seen that the C infinity functions on the whole domain restricted to omega gives a vector space of dense functions in the H1. So that means we can basically work as with smooth functions. The only thing is that the terms which come up in the end must make sense for, let's say, H1 or H2 functions. And as an example, and that is of course the basis for deriving then the weak formulation again, as an example we have, so to speak, generalized formulas for partial integration. And we have come to this formula saying, as we are used to do, we can put an gradient, so to speak, to the vector field, changing the sign and getting an additional boundary integral term with a vector field in the normal direction. And the only thing what we need for this is that the quantities which show up here make sense. So the Q must be, or the components of Q must be L2 functions, the components of the gradient of V must be L2 functions, or that is one possibility. Then the product is integrable, and correspondingly here the divergence must be an L2 function, for which of course it's sufficient that all the partial derivatives are L2 functions. And correspondingly here we need to have a trace of the components of the V and the Q. And all these requirements are satisfied if we say V is an H1 function, the QIs are H1 functions, so we derive first this relation for corresponding smooth functions, of course in the end relying on the Gauss integral theorem, and then we do this limit process. And once having this relation, we can build up further relations like this formula, which says if you have the Laplacian of V, we can bring the divergence over to the test functions in getting this relation. We can get a step further, and not only dealing just with gradients and with divergence and so on, but we can really bring in coefficient functions. That's what we want to do now. We are not satisfied only dealing with the Poisson equation. So we want to have a general elliptic equation, and that means we want to have something of this type. We want to have k times gradient of V and the divergence of this term. We have seen that that would correspond to a term in a PDE describing general diffusive forces. And we can generalize this formula in the following sense. So formally we do the same thing. We bring the gradient here over to the W. So we get this term with change of sign, and we get the corresponding boundary term. And now we have to look at the single components, in which case this does make sense. If we say we want to stick to the situation where, let's first say where W and V is in H1, then we would have here L2 times L2 functions here involved. This is an integrable function, so we have not so much room to multiply with the further functions to stay integrable. Therefore, here we have to assume that those coefficients have to be bounded. Of course, essentially bounded in the sense of Lebesgue measure theory. So, what do we need for this term here? If we take this term as it is, of course we need more. Then we need to have the differentiability of the k times gradient of v. And to do this by the product rule, we need derivatives of the k. So derivatives of the k will appear, and they will be multiplied by u times v function. And if you only take into account that u and v are L2 functions, in fact they are more than L2 functions, I come to this point in a second, then we have to argue in the same way as before. The additional factor, the derivatives of the k has to be L infinity. So for these two terms we are, so to speak, on the safe side if we assume for the coefficients an assumption like that, to be in W1 infinity. That means we have the functions and the first derivatives are bounded. That is what is meant here with this more general Sobolev space, which is where the requirement is not that the functions and the derivatives are to be in L2, but in LP. And with the P we can also go to the limits. Also the spaces have then slightly different properties. We can go the limit p equals to 1, that's very weak requirement, and p equals to infinity, that is then would be the strongest requirement. So the only thing what is left, we have to look at the boundary term. And so here we have justified that the components of k gradient of v as in H1, so everything works here, and because of that we also have no problems with the boundary term. We have now the trace of the components of this vector here, because we have the trace of an H1 function as we have worked out, and that means we have this term in the boundary term. So what is this now? Without the k, we would have had gradient of v times nu. That is the directional derivative in the outer normal direction. So that's what is shortly called the normal derivative. Now it's a little bit different. Now we have the k here in front of that in this scalar product. Of course, we can put the k to the other side. Then it appears as k transpose. So typically for us, the k is symmetric, so that would be just then the k here. So written out in components, this is this term here. And that means we now have, again, a directional derivative, but not in the direction of nu, not in the direction of the normal, but in k, or in general, k transpose times nu. It's a little bit, let's say, tilted or whatsoever. This is what is called the conormal derivative, konormalen Ableitung, wo mir gerade auffällt, ich kann eigentlich auf Deutsch weitermachen, weil unsere nicht-deutschen Zuhörer ja nicht da sind. Dann mache ich auf Deutsch weiter, das ist vielleicht ein bisschen angenehmer für Sie. Oder Sie entscheiden, was ich machen soll. Was wollen Sie? Deutsch oder Englisch? Jetzt haben Sie sich schon so ans Englische gewöhnt? Okay, machen wir einfach Englisch weiter dann. The point really is, from some point on, then it becomes difficult to do the things in German, because then you forget the German names. But I think at this level it is quite reasonable to think in both languages in the terminology. Okay, so this is the argument which I used several times. This is again written down here. If I have an L2 function and I have an infinity function, then the product is again an L2 function. Because if I look at the integral here, this is a trivial estimate. In the integral, I can estimate one of the factors by the maximum norm, and then I just get the maximum norm times the L2 norm. In fact, this could be a little bit weakened, this assumption, and we will see in a second why. But I will not do that. It gets quite messy to write down these weakened assumptions. So in most of the places, the regularity assumptions on coefficients are not optimal, which I'm going to use. So that is the background, or that is one of the reasons why these conditions can be weakened. That refers to the embedding theorems which exist, and we have seen already a trivial embedding. Let's see whether I find it again. Where is the trivial embedding? Oops. It was here, of course, and it's quite obvious from the definition of the spaces. If we just go down in the number of derivatives which we involve, of course, we have not only a subset relation, we also have a continuity of this embedding in the sense that the norm in the larger space can be estimated by the norm in the smaller space. This is the so to speak, obvious embedding. If we would now think of not only of the H spaces, but of the general Sobolev spaces, where the derivatives in LP, then we have two parameters to play. We can go down with a K, but we can also go down with a P. And that means that could mean, and such theorems exist, I'm not going to formulate them, not only this version holds, but because of the fact I'm going down in the L, I can go up in the P here. And that means if I look at an H1 function, it's not only an L2 function, then it's actually an LP function for certain LPs. And this is something which I could have used to reduce the requirements on the coefficients in the aforementioned considerations. But I'm not going to do that. What we are going to do is we want to generalize this embedding. That is another type and much stronger and not so trivial. Okay, in 1D it's easy to prove, and you did this already, or you will do this as an exercise. The fact that the H1 function in 1D are in fact continuous function. On the other hand side, we know that this does not hold true for 2 dimensions and higher dimensions. So there must be a relation between the amount of derivatives we have and the amount of derivatives we give up, this is here 1, so to speak, and the dimension such that such an embedding holds true. And this is given in the following theorem. Here, saying, okay, I have, so to speak, k weak derivatives in L2. I give them all up. I won't only look at the function, but I want to have that this function is continuous and that the embedding is continuous. And I can do that if k is bigger than d half. So I have to give up d halves of my stages of derivatives, so to speak. That would then make a general embedding theorem. And if I don't have here hk, but I have wkp, then the d halves would be substituted by d over p. What does that mean? It's consistent with what we have seen. In 2 dimensions, we would have to give up more than 1. So we don't have a continuous embedding of h1 to the continuous functions, but of h2. So if we want to have, this we will later be reflected on the requirements we have to have on the solutions which we are going to approximate. If we want to have at least that the functions we are going to approximate are continuous functions, and that is a technical point that we have to require that. Of course, it's not very much requirement compared with the C4, C8, or C something what we had for the finest difference method. Then we have to require that the solution is in H2. More than the existence theory provides, then we come in this framework of regularity theory, so we have to see under which conditions solutions which are by definitions only at the first step in H1 are also, for example, in H2. And this embedding theorem then justifies then more. In fact, the result is a little bit more precise than it's stated here. Namely, it says you really use this order. So we go down to the order k minus d halves. So k minus d halves in general is a real number. It's not a natural number. So if there's, so to speak, so for example, it's 2.5, that means there are two derivatives, and there's a half derivative. Half derivative in the sense there is Hölder continuity. Who has heard this word already, Hölder continuity? Nobody? Okay, this is a weakened version of Lipschitz continuity, which all of you should have heard. And in the Lipschitz continuity, we are able to estimate the deviation in the functional values by a constant times the deviation in the arguments to the power 1. And for our Hölder function, say of exponent alpha, it's not to the power 1, it's to the power alpha, alpha less or equal to 1. For example, the square root. If you look at the square root from 0 to 1, including the 0, that is the important point. This is not a Lipschitz continuous function. There's no bound on the derivative. But it's a Hölder continuous function with exponent 1/2. So in this sense, these functions are not only continuous, they are Hölder continuous, but we will restrict ourselves here more to this more simple results. So the only point I'm going to make is there's a lot of room in making the results more precise and more precise and more sharp. Okay, so this we keep in mind. If we have H2 in 2 or 3 dimensions, these are the dimensions we are interested in, then so one requirement would be here k bigger than 1, the other k bigger than 3/2. This is both fulfilled for a k equals 2. So in this case, we have continuous functions. So, okay, this is very basic knowledge about Sobolev spaces. This is really the basics. But I hope, or we will see, for most of the things we are now going to do, this is enough. And so what we are going to do, the first thing is we want to phrase a general version of an elliptic boundary value problem. And then the first step, which takes a while, is to identify conditions on the coefficients and on the setting of the whole problem such that this problem fits into a general theory where the basic ingredients we have already seen in conjunction with our first important results concerning convergence. Namely, we have to have a bilinear form which is continuous, meaning it has this boundedness condition, and which is V elliptic. That is the one requirement, and the other requirement is that the right-hand side, the linear form, has to be continuous also. So let us first state the general elliptic equation. So what do we have? Okay, we have a diffusive part here with a general diffusivity, let's say diffusivity matrix here. So we allow that this function k is matrix valued. Of course, it could be the special case scalar function times the identity. That would be the situation of an isotropic medium acting the same in each direction. But in any case, we want to allow do not want to have here a constant matrix or scalar, but we want to allow that it depends on x. So we want to allow for heterogeneous media which change their properties from point to point. So this is the diffusive part. This part we have considered up till now for k equals identity. Now, in addition, we have seen if there is a flow regime going on and the flow field C, this is now, so this is matrix valued, this C is vector valued. So this vector field, this comes in general from another problem describing the underlying flow, but we only consider here only this one-sided coupling in the sense that this flow influences the solute transport we are looking at if we stay in this terms of application, but not vice versa. These problems vice versa, of course, also exist and are of importance, but that would lead to much more complex problems which we do not consider right now. So this is just a given function, and in the examples we will look at, this will be quite a simple function, but it's a general vector field here. And we have seen convection is described in this term by this given vector field times the gradient of u. So here we have, so to speak, our second derivatives. Here we have our first derivatives, and in addition we include a part with zero-order derivatives, so with the function itself. This can be viewed as a sort of a reaction term. So for positive r on this side of the equation, this describes a sink proportional to the concentration, and for negative r it would be a source proportional to negative concentration. And of course we have our right-hand side f. So this is what we abbreviate with L of u, and this is what we want to deal with now. Okay, and now I phrase several sets of assumptions. You don't have to remember all the details. We can view now at these equations at actually from three different points of view. The one point of view is the classical point of view with which we have started. Everything we have written down must make sense pointwise, and in the end there have to be continuous functions. To have this classical point of view, we need to have corresponding continuous functions for all the coefficients, and that means for this part, of course, if you think this part differentiated out, of course also the derivatives of the case will appear. So this is a little bit badly noted here. Here, of course, also the kij has to be added. Also the kij's have to be, of course, you can think of, can one think of, no, one cannot think of. Not sure whether it's possible to have this requirement without the kij's to be continuous, but in any case, they should be for this point of view. So this would be necessary for the weak formula, for the classical formulation. Then there is the weak formulation which is still to come, which we still have to derive. And we will see that for the requirement, that we can reduce our requirements to these requirements. And that is quite important. So we have to have basically that the right-hand side is an L2 function that is sufficient. So this does not mean that we can allow for something like the delta distribution. You remember this ominous function we have spoken about. This is only possible from this point of view of the theory only in 1D. But of course we can think of quite irregular right-hand sides driving sources. Then for the coefficients, we basically need L infinity. The way we write it, we not only need L infinity for the Ci's, but also for the divergence of C, which is not a big requirement in the sense that quite often flows have the property that they are divergence free, and then that would be no additional requirement. So we have the L infinity requirement on the R, on the Ci's, on the divergence of C, and on the coefficients of the K. But note here, no requirements on the derivatives of the K. That means this allows us now to handle in a rigorous way media, so to speak, laminated media, which are put together, so to speak, piece by piece, level by level, by media with then jumping properties. That is not possible in this formulation. Then we have to write it explicitly as transition with, with individual equations in all the subdomains and with transition conditions and so on. And then we need some further requirements which deal with the boundary and the boundary condition. So we put this back for a second. And then there is an intermediate way to view these equations. The point is, now we can, after we have lost, so to speak, all our shame to deal with derivatives, we can just work with derivatives without doing too much considerations. We can, in principle, we can now differentiate everything, because distributionally every function is differentiable. And we just have to see what comes out, in which function class lies this object which comes out. And in this sense, we can also look at this equation and say, okay, all the derivatives we are going to do, we do first in the distributional sense, and what kind of requirements do we need such that we can really write down this equation as an L2 function then, because f is an L2 function. And you see here, for example, if you only know that the u is an L2 function, then it would be sufficient to have r as an L infinity function. Actually, u is more than an L2 function by these embedding theorems, which I have not made explicit. So actually, we could lessen here the requirement. So we would have something like r in an infinity. And similarly, we can deal with this part. So here we have L2, gradient of u is L2, so we only need L infinity for the c. And correspondingly, we have to differentiate out this term and then see what comes up and what is necessary, that in the end there's an L2 function, and that means we have this requirement. So this is something between this version and this version. We really deal with the original form of the equation. Everything which comes up are functions, but the derivatives are in general weak derivatives, and the equation only holds true in L2. Okay, so then of course we have to have, the whole theory relies on the fact that our equation in the end looks similar to the Poisson equation. That means, for example, we cannot forget this term. If we would forget this term, then we would get a pure advection problem, which is also a model of its own right. But it's, in some sense, it's a very simple equation. On the other hand, it's quite a difficult equation. In any case, it's a totally different. From its mathematical character, it's totally different. So we have to have a condition which says us, okay, the k is varying, the k is a matrix, but nevertheless, the term we have here is similar, and we will see what this similar means to the corresponding Poisson term. And for this reason, we need the requirement, what is called the uniform ellipticity of the operator, which says we need a requirement of this term, of this type here. So we look at the matrix, we look at the corresponding quadratic function here. So we form the bilinear form, we take the vectors the same, xi and xi. And then what is stated here is just the positive definiteness of this matrix. But in principle, this K0, which reflects the smallest positive eigenvalue of the matrix, can be depending on X. So there's a further requirement, namely that, again, there's a lower positive bound of all these minimal positive eigenvalues. That is the uniformity here. Okay, so we require that, what we require is that this matrix is uniformly positive definite in X, and of course we also require that it is symmetric. So let's look what this means. If K is a diagonal matrix, let's say of this type here, then this just means that all these scalar coefficient functions which appear in front of the second order derivatives have to be bounded below by some positive constant. Of course, almost everywhere. It always meant always everywhere. That is the one requirement, and the other requirement basically says we can handle sinks, but maybe it's not possible to handle sources. To write this down as a requirement only in R would say R is greater to equal some R0, and R0 is greater than equal than 0. And by the way we deal with the terms, as you will see in a second, we get this modification in, so we get here -1/2 the divergence of C. But in the absence of advective forces, this says we can handle sinks but not sources. What you can imagine, if you have a source, if you think now from the time-dependent problem, if you have a source, it might not be the situation that the solution exists at all. If you think at the very, very simple ODE, let's say u prime equals u square, then the solution of this ODE only exists on a finite interval of time. So you have an explosion in finite time. So in this sense, it's a very important but nevertheless restricted area of physical models and of possible PDEs we are looking at here. Models which are in some sense dominated by diffusive forces and which are overlaid possibly by advective forces. Okay, now the boundary conditions. Up till now we had just homogeneous Dirichlet boundary conditions. We have discussed already the different other possibilities. We have seen flux boundary conditions, and we have seen mixed boundary conditions. Here we do the classification a little bit different. Okay, we differentiate between 3 types of boundary conditions. So we assume that the boundary is subdivided in 3 subsets, where the third one, the gamma 3, is supposed to be closed. And on this gamma 3, let's start with this. We assume inhomogeneous Dirichlet boundary conditions, so we prescribe the function with a function G3. On gamma 1, we prescribe the conormal direction, as discussed, with a function G1. And on boundary gamma 2, we prescribe a linear combination of the conormal direction and the function value itself by a function G2. So in some sense, the first case is a subset of the second case as long as we have no requirements on the alpha. As long as we want to allow for alpha equals to 0, then of course this case here is involved. We will come to a point where it's reasonable to have also conditions on the alpha, and then these are different cases. So this is the problem we are going to look at. And now we need a weak formulation, and we need requirements which assure that we have a unique solution in the underlying Sobolev space. And the underlying Sobolev space, as we have seen already, will turn out to be a closed subset of the H1 of omega. And this depends on the boundary condition. We have seen already the extreme. The extreme of pure Dirichlet condition means we have to take H1 0. We include the 0 boundary everywhere. And the other extreme would be, as we will see in a second, the Neumann or mixed boundary condition everywhere, where we don't include any boundary condition in the definition of the space. So that is also the very nice thing of the finite element method, or generally of methods which are based on variational formulations. The flux boundary conditions, or the mixed or Neumann boundary conditions, which include flux boundary conditions. And I try to make it clear to you that flux boundary conditions are the real natural conditions. And Dirichlet boundary conditions are something strange, a part of mechanics. They are naturally incorporated in the formulation of the problem. It's totally different with the finite difference method, where we then have to think, oh, how to approximate these normal or co-normal derivatives, how do we do that, and so on. It will just go in naturally, and this is reflected by the fact they do not appear in the space. Okay, so let's start. Okay. Yeah, if we want, okay, to conclude, to finalize that, if we want to have the classical point of view, of course, we have to have that the driving forces and the alpha is continuous. And if we only take the variational formulation, we can be satisfied with L2 function for the driving functions and L infinity for the alpha. Now we can go shortly back. You see here, now you can understand what that means. It means if we are in a situation where we not only have Dirichlet boundary condition, where the measure of the gamma 1 and the gamma union gamma 2 is positive, then we have to have a property of the trace of the normal of V, of this, the normal of this field C times nu on the boundary. We have to have, because it then really explicitly appears in the boundary condition. Okay, so it's not necessary really to track. You could do this, or you should do this maybe then afterwards for a few cases, really to track that everything is okay with the assumptions we did. I hope it's okay. If you find a mistake, let me know. So now we do this thing. So what we have to do, it's quite clear. First we multiply, of course, the equation with the test function. The test function has to be fit to the type of the boundary condition, as explained. Then we do partial integration. The partial integration is now put on a sound footing. As we know, we can do this with H1, H2 functions. Then by this way, the boundary conditions will pop up in the formulation by the boundary integrals. And then we have our formulation, and we have to check the underlying properties of the bilinear form and of the linear form. Okay, and we do this, that we go step by step through a sequence of special cases, and in the end, hopefully, we have covered the full picture. So first case is, that is the case which is a little bit common already to us. We start with the situation where we have homogeneous Dirichlet boundary conditions everywhere. That means, as we know already, we have to include these boundary conditions to the space. That means we have to take as the underlying space the H10 of omega. And now we can go, so to speak, go through these 3 points of view, also with these different sets of assumption. I will not make it too explicit from now on. That's everything in parallel. So what do? We can first do everything classically, in the sense we start with C infinity 0 function, which are dense in the H10, as we know. We do the partial integration here in this term. The boundary term goes away because the V is 0, the test function is 0 at the boundary. So we now get this term. This is more or less the same as we had before, only a k now in front here. Up till now we had gradient u, gradient v. And those terms, they are new. And here we have done nothing. We just leave them as they are. We just multiplied with the v here. And we have the right-hand side. So now let's see whether this machine is still working, in the sense that I can freeze this transparency, and then we can go on. Then you will have it. You'll see it. Okay, let's try to freeze that on this side. Let's see what happens. Okay, it works. So what do we have to check? So what do we see? The first thing is in general we have lost symmetry, because Okay, yeah, good. I can only point to the one which is active. So you see at the left-hand side there are two symmetric components, but of course the middle component in general is not symmetric. So if you change U and V, then there's something different there. So we only have symmetry in the diffusive case if the C vanishes almost everywhere. So that is a point we now have to take into account in the underlying theory, which then gives us a solution. In general, we have non-symmetric bilinear forms. Let's look at the right-hand side. The right-hand side is no problem, because the right-hand side is not only, of course, it's linear, but it's also continuous on our space. This is this trivial estimate. So what is BV? This is the integral of V times F times V. So the modulus can be estimated in this way. And now we just use Cauchy-Schwarz to estimate this L2 scalar product by the product of the L2 norms. The L2 norm of V can be estimated by the H1 norm, and then we see we have boundedness of the V in the H1 norm, and therefore continuity. If we look at that, here we have this reasoning, what we did here. This holds true for any subspace of H1. We have not taken into account the zero trace of this property at that point. Now let's have a look at the bilinear form. Is it continuous? And the answer is yes. So what do we have to do? We have to estimate, now I have to point. You look to the left-hand side and you see what you have to estimate. So we take the modulus, we bring the modulus in. So here we take in this L2 scalar product in RD, which appears in the most left-hand side term. We just apply the Cauchy-Schwarz inequality in RD, which gives us this term. So here, if now one bar appears with vectors, it means the Euclidean norm. So this is either the modulus, as here, or here, or it's the Euclidean norm as here and here and here and here. So this gives us this estimate here. And now we have to go on here. So the next step is, okay, so it will turn out that we can estimate everything in terms of this continuity estimate if we take constants into account, which involve, on the one hand side, the L infinity norm of the Euclidean norm of the flow field. So we need here the L infinity property of the components as assumed. We need the L infinity norm of the R. And we need basically the L infinity norm of all the components of the K, also as assumed. So what appears here is, so K is a matrix. So the first norm is the spectral norm. It's the norm induced by the Euclidean norm. This gives us, so to speak, a scalar function here. And from this scalar function, we take the Euclidean norm. And this is covered by our assumptions, our L infinity assumptions, and this is what we need. Why is this sufficient? So let's go through the estimates. So the first thing is this estimate. I can estimate here the Euclidean norm of this term, matrix times vector, by the induced norm of the matrix times the corresponding vector norm. That is what is stated here. This we plug in here, and these functions here, this scalar function is now estimated by its maximum, so it vanishes in the C1. Correspondingly with the R, it also vanishes in the C1, and correspondingly here with the C vector field, it vanishes in the C2. So we are left with these terms here. So, okay. So the next step is, if you look closely here, what you see here, what you have here again, and you have again here a scalar product, but in R2, so to speak. It's the scalar product of the two vector Euclidean norm of gradient of u, modulus of u, that is the one vector, and correspondingly this is the second vector. Now again applying the Cauchy-Schwarz inequality gives this estimate here. Applying the Cauchy-Schwarz inequality directly here, now let's first stick to this one. Gives this estimate here. Okay, and now we apply the Cauchy-Schwarz inequality in L2. We have a function times function, so we get the square of this function. The square root goes away, the square root goes outside of the integral, and so we get this thing. So in fact, we really got what we would like to see, and what is not yet here on the transparency, it's C1 times 1 norm of u times 1 norm of v. That is the estimate we would like to see for the continuity. So this term, so to speak, the diffusive plus reactive term is okay concerning the continuity. And again, note we have not used that we have this special subspace of H1 that applies to every subspace of H1, including H1. Now we have to use this mixed term. So this term over here, this is a little bit easier. We just apply the L2. In L2 of omega, we apply Cauchy-Schwarz, giving here the L2 norm, giving here the L2 norm. That means we have both, so we can estimate this first term by the H1 norm of u, it's a gradient part, and we can also estimate the second part by the L1 norm, by the H1 norm of v, it's just the function part. Okay, so under our assumptions of this work quite generally, we have continuity of the bilinear form. So continuity apparently is not the problem here. It doesn't require further conditions. The problem, what is a little bit more delicate is, so here it is stated again, so we have checked this and we have not used the homogeneous sterically bounded condition. The considerations apply to every subspace V of H1. Okay. Now we have to check the V ellipticity. So we have estimate u, a at u and u from below. We have to show there's some alpha, some positive alpha, that we can estimate this part by alpha times the H1 norm of u squared. Okay, let's go through a few special cases here. We start with the situation where the C is 0. Okay, so what comes out? So we have left. Now the middle term goes out. The left term can be estimated here by this term. This is just this requirement of uniform positive definiteness applied to the vector gradient of u. Gradient of u at the point x. We apply this positive definiteness pointwise, and then we can estimate the k times gradient of u by in this form. So this is trivial, R0 u squared. So, okay. And now, now of course, we can estimate this from below by the minimum of K0 and R0. Okay. Now, we are not yet ready, because what the problem now which appears is, so we now see two situations. If we only know that the R0 is greater or equal to 0, so it can be 0, it doesn't help us. We have shown the positivity of the form, but not the definiteness of the form. We only estimate it from below by 0, but we have not shown positive constant times norm square. So we need then something which helps us that out of the semi-norm part of the H1 norm, we get the full H1 semi-norm, which in general is wrong. In general, for a general H1 function, we cannot estimate the L2 norm of the function by the L2 norm of the derivatives, take a constant function. But now we have here more than other functions, namely we have here h10 function, and here the Poincaré inequality, Poincaré Ungleichung, helps us, which tells us in the case, and that is the place where we really now use the boundary condition. In the case of an h10 function, let me phrase it in another way, there's a constant which only depends on the bounded domain we are looking at, such that for any h10 function, the L2 norm can be estimated by this constant Cp, so p times, like Poincaré, times this L2 norm of the gradient, so to speak, so this semi-norm out of the h1 norm. But if this is the case, then of course we can, so to speak, subdivide this term in a term where we keep the gradient and one term which we estimate from below by the L2 norm, and so we restore the full h1 norm here, only from the first part, under the assumption of the homogeneous Dirichlet condition. So this is made here. So we subdivide. This can be done in a lot of ways. We subdivide this constant into parts. The one we keep with the gradient of u. The other one we use with the Poincaré inequality. It is made such that those go together, that this constant now becomes the same, and we have now this constant times integral gradient of u squared plus integral u squared. So we get here the one norm square as we would like to have it. So here the homogeneous Dirichlet conditions were essential. Okay. In the other cases, where is it? It will be mentioned probably later. But we can keep it already in mind. What we have seen here, in the case where we would have that the R0 is strictly positive, then we would not have to use this Poincaré inequality argument. Then we could argue for every subspace of h1 of omega that we really have here a positive constant times the h1 norm squared. Okay, so this was now the situation without the advection term. Now we include the advection term. And we start with smooth functions, the infinity zero function. Because of density, this is sufficient for the transformations, and then we can justify by the density argument the outcoming formulas for the general situation of H1's functions. So what do we have to look at? In the case of the gradient of the advection term, we have to look at this term, C times gradient of u times u. But gradient of u times u is just 1/2 gradient of u squared by the chain rule. So we plug this in. Now we have a gradient here. And now we can apply integration by parts and bring this gradient over to the c, so we get here the divergence of c in the formulation. No boundary terms because we are in C infinity 0. By density, we can justify this relation in general. Well, what does that mean? That means the gradient, the advection term, so to speak, has now vanished and has transformed itself to a reaction term, to something which we had already in terms of this r times u times u. That means the only thing what now happens, we have a modification of the r, and therefore also the condition appeared for a modified r, namely for r minus 1/2 gradient of c, divergence of c. You see it here again. So now with this general definition of R0, we have again this estimate, and we have again all the distinctions. So in the case if R0 is strictly positive, we are done, in general done. We have to be a little bit careful because for the transformation we also have used that we are in H1 0. We have not looked at the boundary term, so we have to come back to this one later on where we don't have the Dirichlet boundary conditions. And again, we can say, so either we rely on the Poincaré inequality, only looking at this term, then it's sufficient that this R0 is greater or equal to 0 or otherwise. So put it together, we have now checked that in the case of homogeneous sterically boundary conditions, we have a variational equation which has a continuous and V elliptic form, in general not symmetric, which has a continuous linear form on the right hand side, and these were the conditions of the lemma of Lax-Milgram to assure that there is a unique solution. And now we have the framework which tells us there is a unique solution, so now we could start with approximating them. But of course we want to look at the other boundary conditions too, so we now have to go step by step to the more general boundary conditions. So now we do the other extreme case where the whole boundary is gamma 2. That means everywhere we have these Neumann boundary conditions prescribing the conormal derivative. And in this case, we can take, or we have to take, as the ansatz space, as the underlying function space, the full H1. So no boundary conditions in the space. And why is this? Now we do the same thing as, gamma 2 is we have mixed boundary conditions. I have to correct myself. Mixed boundary conditions, not Neumann boundary conditions. But as long as we don't have assumptions on the alpha, the Neumann boundary condition is included in the mixed boundary condition. So let's do the same thing, and the only difference what appears is if we do now the partial integration, we cannot restrict ourselves to the ones to the C infinity 0, so we get a boundary integral in. And the boundary integral which we get in is, let's go back to the definition of the boundary condition. So we are now looking at this case here, and the boundary integral which we get in, it depends which side of the equation we are talking. Let's talk of the left-hand side, where, so to speak, the unknowns are. And there we get a boundary integral which has the form minus, which involves minus k times gradient of u times nu. But what is this? This again is alpha times the test function. But this, what is this? This is alpha u times the test function minus g2 times the test function. So we get from this part here, if it exists, we get a bilinear contribution, something which has to go into the bilinear form. And from this part, from the data, we get something which has to go to the right-hand side. And doing that, we get here, okay, this is not very nicely printed, we get here this additional integral. It's now a boundary integral, alpha times u times v over the boundary. So there's a d sigma to indicate that this is a boundary integral. And in addition, for the b, get this additional part, boundary integral g2 times v. So now it's clear what we have to do. For the continuity, both of the a and of the b, we have to check what these additional terms bring with them. And additionally, we have to see what is the situation with the V ellipticity. We have to check under which condition this additional term does not make us any harm, or maybe under which condition this additional term helps us. Let's start first with the continuity. So we have to estimate first this term here. Assuming that the G2 is in L2, we can again estimate by the L2 norms. Here the L2 norm of the trace, and the L2 norm of the trace can be estimated by the H1 norm on the full domain, so we are done with this part. And correspondingly here with the continuity, assuming that the alpha is an L infinity function, we can estimate this triple product by L infinity, L2, L2, and the L2 norm of the traces again by the H1 norms here, again using the trace theorem, and again we are done with the continuity. The interesting part again is the V ellipticity, and now we have to modify this transformation of the advective part, which we did, because now we get a boundary term in this transformation. So let's do it again. How was it? We had this advective part with the same arguments, u and u. We would like to rewrite this as 1/2 gradient of u squared. We would like to do this partial integration here. That's as we had it up till now. And then now we get additionally this boundary terms 1/2 nu times c, so the normal of the flow field times u squared. If we now plug this in, that means we not only get a modification of the r here, to r minus 1/2 divergence of c, as we have seen already, we get also a modification of this alpha part here. And this means, to make sure that this additional boundary term does not do us any harm, we must be able to estimate this from below by 0. And that just means we need the requirement alpha plus 1/2 nu times c is greater or equal to 0. Okay, but now we are in a situation where we cannot rely on Poincaré's inequality. We don't have Dirichlet boundary conditions. So now we need something different, which really gives us coercivity. And one possibility would be to say, to rely on the fact that R0 is positive. Then we have here a positive contribution, we have here a positive contribution, we have here the full H1 norm. This term does not disturb this estimate, so we are done. In the case where R0 is only greater or equal to 0, including the extreme case being 0, we only have the semi-norm here. Now we need something different as similar to the Poincaré inequality, which helps us. And this is a generalization of the Poincaré inequality. That's the so-called Friedrichs inequality. The Friedrichs inequality says the following. If we have a bounded Lipschitz domain, so the same assumption as in the Poincaré inequality, and we have some subset of the boundary with positive d-1 dimensional measure, then there is a constant Cf now, such that for all H1 functions, we have an estimate of the H1 norm by the semi-norm including the semi-norm taking care of the derivatives, plus an L2 boundary term over this subset with positive measure here. And you see, first of all, Poincaré is included. If we now, or Poincaré is sharpened in the sense that we now have a version of the Poincaré inequality which says it's not necessary that the function vanishes everywhere at the boundary. It's sufficient that we fix a subset of the boundary of positive measure and look at those functions which vanish at that subset. And as you remember, if you have done this already, I'm not sure whether when it was issued, if you've done this corresponding estimate in one dimension, it was only necessary to fix the function to 0 at one point, not at both points, to get the one-dimensional Poincaré inequality. Okay. So let's take advantage of this estimate and then, so to speak, opposite to the assumption that K0 is positive, that R0 is positive, we can take into account that the lower bound of this term here brings in something. More precisely, what we have to have is we have to have now such a subset of positive measure, gamma tilde, where this alpha plus 1/2 normal component of C is bounded from below by a positive constant, alpha 0. Then we get an estimate which includes the semi-norm here, and which includes this L2 boundary term, and this is enough, as we have seen, to estimate. This is now again cut off here. I'm not sure whether it's cut off on the transparency or cut off by the projector. I would assume the last version, but anyway, what is given here, this is of course C5, the new constant, times 1 norm of u square. And what is this? This is the factor we had already, and the factor which comes in by applying the Friedrichs inequality. Okay. So now we have dealt with a situation, so to speak, with the two extreme situations, Dirichlet, homogeneous Dirichlet boundary condition and mixed boundary conditions including pure Neumann boundary conditions. That was the situation, and where we had two situations. So either we rely on the fact that the R0 is positive, then we can include Dirichlet boundary, pure Neumann boundary conditions. So you remember our discussion of the Poisson equation with the pure Neumann case. And we have said, okay, this is special, and in this sense it's not included here, because in this situation, first of all, we need a compatibility condition of the data to have a solution. And then in the situation where we have a solutions are only unique up to a constant. So both situations are, so to speak, not valid. We don't have a solution in general, and we don't have a unique solution. Also, this case can be included here by a modification of the forms. But what we have seen, this is not the case if we, for example, would add such a sinc term to the Laplacian. If we would not look at the equation minus Laplacian of u equals f, but to the equation minus Laplacian of u plus u equals f, for example. Then we have again our V ellipticity, then we have again uniqueness of the solution, unique existence of a solution. That is this R0 positive case. And the other version would be not to rely on the on this zeros order term, but to rely on the boundary condition. That would be the alpha 0 positive case, and that would mean, okay, we stick to the Laplacian, but we don't look at pure Dirichlet boundary, pure Neumann boundary conditions, but we have, at least at a part of the boundary, we have a mixed boundary condition. That again gives us unique existence of a solution. Okay, now the general case. Okay, we're not yet done. We look at the general case, but we only allow for homogeneous Dirichlet conditions. We have seen the mixed and the Neumann boundary conditions, they made no problems. They were incorporated quite naturally, therefore also called natural boundary conditions, in the form, if you have a mixed boundary condition, or just in the right-hand side. What does that mean? In the extreme, on the extreme, if you have a Neumann, if you have homogeneous Neumann boundary conditions, you don't see the boundary condition in the formulation. It gives no contribution to the Berliner form, and it gives no contribution to the right-hand side. So forgetting the boundary condition, so to speak, is just saying I use the homogeneous Neumann boundary condition. Okay, so now including the Dirichlet boundary condition, and this we have to do in two steps again. First, only the homogeneous case. And now we know already what we have to do. We have to include this boundary condition into the definition of the space. But now we have the homogeneous boundary condition only at a subset of positive measure. So this here is the appropriate space to look at. We have the h1, but we have only those functions from h1 of omega where the trace as an L2 function on the boundary vanishes in gamma 3. So what is this? So we have the trace operator. The trace operator is a continuous operator, as we have seen. What do we do? How is this set defined? We can say what we are looking at here is the pre-image of a Urbild is the pre-image of a continuous operator of a closed set, namely the set consisting only of the zero function. The zero function. So what is the operator? The operator goes in two steps. First the trace operator, then the restriction of the trace to the subset gamma 3. That's also a continuous step. If you reduce we're talking about L2 function, you reduce the domain. That's a continuous step. And for this operator, now we take the pre-image, the Urbild of just one function, namely the zero function. In any case of a closed set. And what is the pre-image of a closed set under a closed operator? What is this? Characterization of continuity. It's also closed. You can say, instead of taking these pointwise definitions of continuity with which you have started, you can say a continuous function is just a function which has the property the pre-image of every closed set is closed. It's a typical functional analytic argument to show that a set is closed. So we are talking here about a closed set of the complete Sobolev space H1, and a closed vector space, subspace of a complete space is complete. So this is also easy to show. Maybe we can also do this in the amendments. So in any case, we are talking here again about, which is of course of importance, of a complete vector space. We are again talking about here about a Hilbert space as the underlying space. Okay. So that is basically what I said. What I said is written down here. And what does that mean? Now we proceed as above. And what do we get? In the partial integration, what does it bring in? It brings in, for gamma 2, it brings in this contribution on the in the bilinear form. It brings in the contribution in the right-hand side, in the linear form, also for the gamma 1. And for the gamma 3, for the Dirichlet boundary condition, it doesn't bring anything, because homogeneous boundary conditions. So now, okay, what does that mean? The continuity, there's nothing changed. We have exactly the same, the additional terms, and we have seen already what kind of assumptions we need to ensure that the B and the A is continuous. And now we have to have a small look at the V ellipticity. And now, okay, things become better. Things become easier in this respect. Because we can ignore that we have these Dirichlet boundary conditions. We can argue as if we would have the larger space H1 of omega, and here we have seen conditions which give us the V ellipticity. But in addition, of course, now we can use the Friedrichs inequality, and so we do. Okay, we do again the same computation we did before. We again get this part here, and we get again this modification both of the R term and of the alpha term as to be seen. But as we can now use the Friedrichs inequality as a generalized Poincaré inequality, the only thing is that those terms which come, yeah, okay, there's one further point which I have missed. Now by this partial integration, if we really have also Neumann boundary conditions, we get also this additional term here. There, so to speak, this is the situation where the alpha is 0. So this is the alpha plus situation in this case. So we can now say it's enough that this term and this term does not do us any harm. So we have to estimate that from below by 0. For this, those assumptions are sufficient. We have to estimate this thing from below by 0, and this semi-norm term now is sufficient to, via the Friedrichs inequality, via the generalized Poincaré inequality, to bring in the coercivity. Okay, now let us, here's this special case of the Friedrichs inequality which I use, which I have indicated already. If we are in a situation, we have a subset of positive measure, we consider functions which vanish. At this subset, for those functions, we have uniformly a constancy f, only depending on the domain, which allows us to estimate the L2 norm by the H1 semi-norm. I'm not sure what this is here supposed to be. That's basically the same thing. Yeah, this doesn't make sense. It's the same. Yeah. Okay, yeah. So we get the same situation, we get the same results with these additional sign conditions as in the case of the homogeneous, the fully homogeneous Dirichlet case. So let's collect what we need. It's not to be remembered, but it's quite natural. So if you have some feeling for the problems, you don't have to remember these conditions. They are quite natural to write them down. But anyway, so what did we see what we need? We need the sign conditions. We need the sign condition for the modified source term, sinc term. We need the sign conditions for the normal of the V or for the normal of the V plus alpha here on the corresponding boundaries. And additionally, we have to have something which in the end really brings, this would be the level which gives us in general only positivity but not definiteness of the form. Now we need something which in addition gives us the definiteness. And this can be, as we have seen, a little bit of Dirichlet boundary condition, and it can be a little bit of strict positivity of this function, or a little bit of strict positivity of this function, or a little bit of strict positivity of this function. A little bit always means there's a subset of positive measure and so on. Okay. This is now a sufficient set of assumptions under which we can work, which assure us the existence, the unique existence of a solution. It's sufficient but not necessary. The conditions can be weakened with other techniques. Let me make a few comments on that. So one thing with other techniques, one could see that this positivity can be lessened in the sense that only the measure of the set where the positivity, where the function is strict positive, has to be positive. So it's not necessary to really have a uniform lower positive bound for those functions. That was now convenient for us really to estimate those integrals which appear and come up with a positive factor times L2 norms. That is one remark, and the other remark is what we did till now is if we had a critical term with set, okay, we take care that this critical term does not do us any harm. So we want to estimate it from below by 0. That it does not disturb our strictly positive terms, our positive factor times norm squared terms. But of course, one could also say, I have here a very nice positive term with a big alpha. Of course, I can use this to balance an, so to speak, a negative term. But this would lead then to requirements which really involve combinations of the constants, and in this combinations also the constants from the Poincaré and the Friedrichs inequality will come up. So in a specific case, one can do much more, one can allow for more situations, but to write this down in general would get quite messy, and therefore I avoided that. Okay, what is a little bit strange at the moment, those conditions here at the boundary. Why this part, and why in particular this part with the 1/2 here? It looks a bit strange. Okay, it comes up from the partial integration, but if we change a little bit the formulation of our problem, then those requirements become very natural. And that is the next thing I would like to look at. If you remember the very first derivation of those models, which we did, actually the model was not really in this form which in which I have written down. It was not only in the form where the divergence. So what we had till now in our formulation, we just had the divergence for the second order part, and that was the only place where we did partial integration. And all the other parts had no divergence in it. That's a little bit more general formulation, but as you remember, the natural way those things come up is that there's a divergence of the transport operator. And the transport operator consists of the diffusive part and of the advective part. So that would be the more natural formulation. It's restricted compared to the other, because if I now differentiate this out here, this part, the divergence of c times u, I get the c times gradient of u, the term we have looked at before, and in addition I get the term divergence of c times u. That means if I now modify this r tilde to the notation we had up till now, to this r, we are now in the formulation we have looked at. Now let's apply our assumption for this special case, where the r has this special structure, divergence of c plus some r tilde. And now I formulate boundary conditions which are quite natural. I forget about the Dirichlet boundary conditions for a moment, they can be included. I only look at two types of boundaries. The one, gamma 1, I call an outflow boundary, Ausflussrand, and the gamma 2 I call an inflow boundary, Einflussrand. And there should be exactly what the names say. That means the underlying flow given by the vector field C should be such that at gamma 1, at the outflow boundary, it should it should have the property c times nu being greater or equal to 0. That is, there is a oh, now I'm missing the English word. There's ein spitzer Winkel, an angle below p half between the flow direction, c, and the normal direction. So the flow does not need to go out in the normal direction, but it has to go out. So the extreme would be tangential flow. And vice versa at the inflow boundary. So let's do this assumption, or let's do this definition of gamma 1 and gamma 2, and you will see that the notation is consistent with the notation we had till now. Remember, gamma 1 was the Neumann boundary condition, and gamma 2 was the mixed boundary condition. Let's see how this again comes up. Now I have to formulate, at these boundaries, I have to formulate the boundary conditions. Let's begin with the gamma 2. That's maybe easier to comprehend. So what we do at gamma 2, at the inflow boundary, we just prescribe the total influx. The total influx in normal direction. So what do we have here? We have here the flow field, Cu, convective part, minus K gradient of u. Diffusive part, we have minus V, so the inner normal. So we prescribe the inflow in direction of the inner normal. And at the outflow boundary is a little bit more tricky in the sense that in the pure advective case, that would be the part where we would have no boundary conditions whatsoever. that means for example, what we cannot do is we could do Dirichlet boundary conditions at the outflow boundary. That would lead to other things, that would lead to so-called boundary layers, because then we would produce a conflict between the value we impose violently for the solution and the value which is, so to speak, transported by the equation. And to have this transported value as undisturbed as possible, the following boundary condition is reasonable. We are saying, okay, there is the total flux coming from the interior, and there is a total flux from the outside. And this total flux from the outside, both in normal direction, and this total flux from the outside only has a convective part. So the medium ends there, that it triples out or something like that. That would be a visualization of that. And in addition, we assume that the, let's say, concentration is continuous over the boundary. So the u which appears here is the u which appears here. And now you see those terms just cancel, and what is left is just a homogeneous Neumann boundary condition. So a homogeneous Neumann boundary condition is a reasonable condition to be posed at such an outflow boundary. Okay, so in this sense, both Neumann boundary conditions and both mixed conditions come up naturally. Here we now have a mixed condition. You see, we have here the conormal derivative, and we have a term alpha times u, and alpha is just minus c times nu. And if we now plug this together and write up our conditions, so the first condition, this r minus 1/2 divergence of c, becomes r tilde, because now we add here the divergence of c, plus 1/2 divergence of c. And on gamma 1, the conditions becomes what we have to impose a nu times c greater or equal to 0, but this we have imposed in any case. That is the definition of the inflow boundary. So this definition becomes natural. This requirement becomes natural. And also at the, the definition at the outflow boundary, requirement at the outflow boundary. And at the inflow boundary, we have a sign condition on alpha plus 1/2. Normal of component of c. Alpha was normal component of c, a minus normal component of c, sorry, and so this becomes minus 1/2 normal component of c, and now again the corresponding sign condition is the sign condition of the inflow boundary. So for this setting, the sign requirements we have posed on these normal components of c become natural. They are just fulfilled by definition. And this stronger requirement saying this is not only, these functions are not only non-negative, they are only bounded below by some positive constant, just basically means we include the tangential flow. Just says, okay, there's really some inflow. It's not, in principle, at the moment, it's allowed that everywhere is tangential flow. That means no flow in the normal direction. And these stronger requirements just say, okay, there's really some inflow and there's really some outflow. So this is quite natural conditions. Okay, so what is left? Possibly, let's say whether I can do it very quickly. What is left is now the inhomogeneous Dirichlet boundary condition. So the problem is, what we want to find a solution of some PDE, doesn't matter how it looks, such that the trace of this function, of this h1 function, is a given function on this part of the boundary gamma 3. But we know already, or I said it at least, that the functions which appear as a trace are not the full L2 space. They are it's a smaller closed space, which is also then called h1/2, but that's just a name at the moment. So this is really a requirement for the G3. So we cannot just say, let G3 be an L2 function. Then it might not be possible to represent this as a trace, and of course then it cannot appear as a solution of a problem. So the basic requirement to have a solution is that the G3 appears as some trace of some omega from H1. Okay, so we take such a function. Okay, at the moment it's not clear how to take it. Later on we will see that's not a practical problem. But what we can now do is we can, with the help of this function, we can, so to speak, shift the problem. What we would like to have is we would like to have a solution U tilde from H1 of omega. This U tilde we write as this function W and a function, no, it's a bad notation with the U tilde because it's used twice, I think. Okay, we assume the assumption of this element W, and this means that the requirements we have can only be set. We are looking at those functions as possible values of the possible candidates for the solutions, which have the same trace. Having the same trace means, because of the linearity, V minus U has trace 0. That means V minus U has to be in the Sobolev space, including the homogeneous boundary condition. So V is now the space with a homogeneous boundary condition, and what you see is we are looking for a solution now which is not in a linear vector space but in an affine vector space. It is this space with a homogeneous boundary condition shifted by a fixed function. As a solution of an inhomogeneous set of equations, of course, is also not in a linear space, but only in an affine space. Okay, so that means if we're now looking at a solution, and this, what we now can do is we say we look for the solution in V tilde, this affine space, but this doesn't matter too much. What we do is we write this U tilde in form of a V times W, and that is we go back to our now linear space, which we also use as a test function. You see here the asymmetry. Here we have the V tilde, inhomogeneous boundary condition. Here we have the V, homogeneous boundary condition, which we need to get rid of the boundary term. And this asymmetry does not fit in our formulation, so we have to get this away. So we have to make a V out of this V tilde again. And that we do, we just subdivide the U tilde, as I said, in a U and in this fixed W. The U part we keep here, and the W part, which is just a linear part because the W is fixed, goes over to the B. That is, we get now this formulation, and the only thing what has changed is that we changed the definition of the right-hand side with this part here by the W, which is, of course, again, a linear and continuous part, so nothing has changed with the condition. The only thing which we have to think about is how do we realize this numerically? This sounds pretty complicated in terms of a finite element code. Find such a function W, subdivide this part. It will turn out it's no problem whatsoever. Okay, so by this we have finalized this setting, so now we can really do general finite elements for this kind of problem, and this we will do then from next week on. Okay.